Today I want to talk a little bit about the Arrhenius equation, which is relating kinetics to temperature, which is a pretty intuitive relationship because we know that if we heat things up, that speeds things up. That's kind of this kinetic molecular theory, that there's this direct relationship between the heat and the movement of particles, and that's kind of how we define things like phases of matter and such. And kind of conversely as well, if I cool things down, then that's going to slow down the movement of particles. If you slow down the movement of particles, you slow down how much they collide together, which gets into collision theory and this idea that chemistry happens because of the collision and orientation of particles in the right way. And so the Arrhenius equation gives us a way to relate that rate, which we can really kind of think about in terms of that rate law constant, because if you change that rate law constant, you change the rate and the temperature. So how does that relate? Because most of what we've talked about so far is the relationship between the concentration of reactants and the rate. So how does that change? Well, it does have an impact, but so too does temperature, and that's where Arrhenius comes in. Svante Arrhenius is someone that we see in chemistry in a number of different areas. He's the one who came up with the ionic theory of solutions. He was also one of the first people to recognize and really study the impact of carbon dioxide on warming. And that kind of gets into this idea of relating temperature to kinetics, because that's where a lot of the early atmospheric kind of chemistry came from. So Svante Arrhenius was a Swedish chemist. He's one of those ones that's a physicist. You'll see this a lot in my videos, that I talk about these physicists that I just sort of claim as chemists, and Arrhenius sort of fits in that category as well. Kinetics and the movement of particles really does fall in a physics kind of realm, and when we're talking about speeds of these things happening, things like root molecular speed, and thinking about the movement of individual particles and how the energy of those collisions can cause chemistry, that's a very physical kind of realm in the realm of physics. So there's a lot of overlap with the chemists of the time. So this is the Arrhenius equation. So Svante Arrhenius is relating the rate constant, K, so that's the same K that we see in our rate law expression up here, to A, which is called the frequency factor. And the frequency factor really combines together a lot of the things that we see in collision theory. So collision theory says that that there's kind of this motion and speed of particles, and how often these particles collide is going to give us an indication about how efficient the chemical reaction is going to occur. So the frequency factor really factors in kind of how often these things collide together, and also the orientation of the particles. So kind of the orientation, because just like with our Velcro, if I put together two of the loop ends of my Velcro, then that's not going to cause any stickiness, but if I do the loops and the hooks, then it sticks together. So that's what this frequency factor is taking into account. So how often are the particles going to be oriented the right way, and how often are they going to be colliding together? Now, for a given reaction, that frequency factor, this capital A, is going to be a constant. So it's really dependent on the reaction itself. So kind of what is the condition of that reaction? What are the things that we're looking at? How complicated would they have to orient themselves in order to make the chemistry occur, in order to break bonds and make bonds? The frequency factor takes into account all of that. And we're not going to get into the details of how that gets calculated for things. Save that for future things. All right, E sub A here is my activation energy. And activation energy is the amount of energy that it takes, the minimum amount that it takes for a reaction to occur. So that we think about a reaction progress as kind of like a hill, and to overcome that hill in order to get from reactants to that kind of transition state or that activated complex, then we have to overcome the activation energy. And then once we overcome that hill, then because we get energy out when we're forming these bonds, then it's just kind of a natural progression. So this is really the barrier that it takes for a reaction to occur. How much energy has to come from these collisions in order to overcome that hill. And then R here is the same R that we've seen with our gas laws, Because we're talking about energy, then we use the format with joules. So that's the 8.3145 joules per mole Kelvin. You can, of course, convert that to kilojoules. With the way that this is set up, if you use this format of R, then that would mean that your activation energy has to be in joules as well. So just make sure to kind of keep the unit straight in your head there. And then T, of course, is my absolute temperature, meaning that it has to be in Kelvin. So essentially this says there's a relationship between the rate constant, which is my K. It's related by this frequency factor to e to the negative activation energy divided by the rate, the gas constant, and the temperature multiplied together. So what this says then is as the temperature increases, then the rate constant increases. Okay, that's what we get out of this. Now, this is kind of a hard equation, I think, to kind of unpack physically. I think it's actually easier to see and to think about if we were to maybe graph it. And so in order to graph something like this, it maybe would make sense to take the natural log of both sides to get rid of this e to the x, right, where x is equal to the negative activation energy over the RT. So if I was to undo all of this and take the natural log of both sides, then I'd end up with the natural log of my rate constant is equal to the natural log of my A, my frequency factor, which we know is going to be a constant for a given reaction. And then plus my negative EA over RT times negative ER. And I'm going to unpack my T here. So instead of putting it here, I'm going to stick it out here by itself. And the reason that I'm doing that is because one of the things that we can do is we can graph the natural log of our rate constant versus 1 over our absolute temperature. So where we have our natural log of K on the y-axis and our 1 over our temperature, our inverse of our temperature on the x. And if we graph these, then what shakes out of this is then I have this is my M, my slope, and then this is my B, where my y-intercept here. So the cool thing is that my slope here is equal to the negative activation energy over R, and R is a constant. So if I can graph these data, if I'm given temperature and a rate constant, then I can use the slope of that line to give me my activation energy. So that's kind of a neat way to solve for an activation energy. When we ask how much do we need in order to make a reaction occur, then this is a cool way to be able to do that graphically. Now, another way we can do this using the same kind of idea is what is called the two-point Arrhenius equation. So the two-point Arrhenius equation looks like this. And again, it's the same idea here. That's the reason that I talked about it graphically here, is if I take the ln of K, but now I'm looking at the ratio of K, so I'm given 2 rate constants, given 2 temperatures, then I can use those 2 data points to get at either the activation energy, or if I have the activation energy, I can figure out one of the temperatures, or I can figure out the rate constant at one of the temperatures if I know both temperatures and the activation energy. So this is kind of a handy way. So this combination of the Arrhenius equation and then this two-point Arrhenius equation that comes from that kind of thinking about this on a graph sort of way are really useful. So let's think about these in the context of some actual data. So let me give you a data set here for the decomposition of dinitrogen pentoxide. We use a lot of nitrogen and oxygen containing compounds for kinetics, which is handy because they do a lot of gases, and a lot of them are pretty simplistic in terms of their reaction mechanisms. So we can think about this decomposition reaction of my dinitrogen pentoxide, and we collected some data. So using my two-point Arrhenius equation, let's use these 2 points. So let's use 1 and 2 here. Then we can find the activation energy. So the way that we would do this again is we have the natural log of K2 over K1 is equal to the EA over RT, oops, yeah, over R, and then we're breaking out our T's here. I'm just going to make that mistake the whole video. That's just going to be that's what I do. So I'm just going to try to stick an extra T in there. All right, so we know that R is a constant. So we have our R, 8.3145 joules per mole Kelvin. We're finding EA, so that's kind of my unknown. And we're going to use these 2 points. My temperature is already in Kelvin. My K's are in per seconds. So I can take the natural log of my K's here. Let's use my K2 over my K1 is equal to my EA over my R. And then times my temperature. So here's 1 minus 2. Now, depending on how you like to do these things, as you've seen in some of my past videos, I actually prefer to rearrange this thing. So if I was doing this, I would multiply both sides by R. So I'd have R times the natural log of this ratio divided by this whole quantity. And then I would plug in my numbers. Some people are more comfortable plugging in the numbers first, solving down and getting more numbers, and then solving for whatever's left over. Whatever your comfort level is with the algebra is fine. However you need to manipulate it. I would probably do this all as one number, just to make sure that you don't forget to take the inverse of things and make sure that your numbers have magnitude that makes sense, etc. So we ultimately end up with an EA that is equal to this number. Now again, because of the units on my R, this is going to give me units of joules for my activation energy. Because we're limited to, looks like 2 actually, sig figs from our K, then we'd probably be using fewer. If we keep 4 from my temperature, that would give me kind of 103.6 kilojoules. If we were just doing 2 significant figures, we'd do 1.0 times 10 to the second kilojoules. So that would be fine too, kind of depending on which ones we're taking into account. So here's our activation energy in kilojoules. What this tells us is that in order for this reaction to occur, then I need to put in 103.6 kilojoules worth of energy, and that energy comes from colliding particles. So these things have to bash themselves together with this amount of energy in order to make this reaction occur. Okay, given kind of these temperature ranges. And if we have larger swings in temperature, then this is going to have more of an impact, and we can solve for that too. So another thing we could kind of say then is, well, what would the rate constant for this process be at a temperature that's not on the list, right? Well, I could say, what is the rate constant going to be at 350 Kelvin? Then I could go back to the original Arrhenius equation. K is equal to AE negative EA over RT. Right? And if I was thinking about it this way, then if I have the activation energy and I have, my temperatures, the thing that I'd need to figure out is my frequency factor, and then I could figure out kind of what the rate constant would be from there. So that would be another way to go. And these frequency factors are look-upable. This isn't something that you would know off the top of your head. This would be something that you'd have to be given information about, or it'd be something that you'd have to find. Okay, and the other thing you could do is if I had 350 Kelvin, you could plug that in and kind of play around with that too, where one of your K's is the unknown, and you could use another one of these data points to compare to. So lots of options, lots of ways to solve for these things. All of this interconnectedness with the 2 different Arrhenius versions, the Arrhenius equation and the 2 points using data and graphs. And that's the relationship between temperature and rate constant. If you have questions on that, don't hesitate to reach out. Otherwise, I'll talk to you again soon.